think it has some interesting mathematical physics and also some interesting qualitative feature that we learned about bosons on lattices. And I want to emphasize that lattice bosons in some respects are very different from continuum bosons. The lattice introduces quantum effects that modify especially the dynamics of the bosons. And the dynamics of bosons are seen in the transport properties and in the vortex dynamics. Vortex dynamics are the transport properties in the presence of an external magnetic field or a rotation. So the interesting effects will be discussed shortly. I'll do some short review on the vortex transport theory. It's well-known stuff that is for background. And then define what the models of lattice bosons that are interesting. And then we look at the interesting points of the phase diagram of lattice bosons. And the most interesting point in this talk will be the half-filling of the lattice bosons. And we'll study them on the gauge torus. Essentially, it's periodic boundary condition, a square lattice of lattice bosons on a periodic boundary condition with our Bohm fluxes. And that way we can define vortex wave functions and calculate their mass. And we find interesting quantum numbers that are associated with the vortices of hardcore bosons. They're called V-spin, SU2 quantum numbers. And then we'll talk about calculating the Hall coefficient of bosons and seeing interesting features that are not familiar from the continuum theories. So as I said, there's a bunch of papers dating quite back into the dynamics of vortices, but the most relevant to this talk is the last two papers, this Physio letter and the long paper that will appear shortly in Physio B, that's on the archive already. So first, I come from the field of strongly correlated electrons systems, and the most interesting of those systems are the high-temperature superconductors, and that's where I got interested in bosons. The reason, when you think about superconductors, you don't really think about bosons, you usually think about paired electrons, but the BCS wave function assumes a large parameter, which is kF times the coherence length, to be much larger than 1. It's essentially the Fermi energy divided by the gap, and that means that the BCS wave function is not really well described by bosons, but in terms of pairs that have a very large coherence length or sizes which overlap. And if you look at the coherence length as measured experimentally in many of these materials, the coherence length is measured in microns, while the Fermi wavelength is measured in angstroms or in nanometer scale. And therefore, these materials, which are called traditional superconductors, are well in the BCS regime where kF size much larger than 1. Their core size contains many states, called Lejeune states, and these are the traditional superconductors. But if you look down here, families of superconductors which are called unconventional in many sense, the unconventionality can be traced to the fact that they have very short coherence length, which means that in fact the size of the pairs is approximately the distance between the charges. And when you look at this regime, the core size is very, very small, contains very few states in it, and it is quite sensible to think about these superconductors, their transition temperatures, and also their normal state properties above the transition temperatures, not in terms of Fermi liquid theory, but in terms of bosonic theory. But these are strongly interacting bosons, and in fact, they are hardcore. You cannot put two Cooper pairs on top of each other because of the Fermi statistics, in fact, but they're hardcore bosons, and they fill the lattice. The superconductors are placed on square lattices, and the bosons feel the effects of the lattice quite strongly. So that's why I'm interested in lattice bosons. But of course, they have much better representations in cold atoms, and this is the famous Bose-Hubbard model that treats essentially interacting bosons on the lattice. And this is the famous phase diagram that's been worked out in mean field theory and confirmed with much more sophisticated Monte Carlo simulations. The phase diagram includes the weak coupling limit where these bosons could be considered as free particles, and then a continuum theory works quite well to describe their dynamics in the order parameter, and that's this region of weak coupling where you have a good superfluid with phase order. But as you go to strong coupling in this regime, there are these phases that do feel the lattice very strongly and do feel the strong interactions, and these are the commensurate mod phases where you have an insulator of localized bosons. And this is a very interesting quantum critical point between the superfluid and the mod phase. And if you want to describe the region of that quantum critical point, it is sensible not to keep all the degrees of freedom in this model, but to keep only, let's say, n, in this case 2, and 1 above and 1 below densities. And if you look at this local Hilbert space of just 3 occupation numbers instead of 0 to infinity, you could think of describing the excitations of this system using spin 1. Spin 1 degree of freedom. And indeed, you can describe this phase transition using rotator models or XY models with odd number of states. Now, I'm interested actually in this regime. This regime is even more strongly coupled, but the density is between 2 integers. Let's say between 0 and 1. Between 0 and 1, if I keep only 2 states, I have effectively a spin and a half to describe my low energy excitations. I do have a superfluid here, because if I put a small number of bosons on the lattice, even though they're hardcore interaction, you do get superfluidity. But, as you can see, the lattice plays a very important role, and they're effectively introducing hardcore constraint, keeping my occupations only in 2 values. So, what is the effective model that describes this regime? It's the quantum XZ or quantum XY model of spin and a half. And it's important to remember it's spin and a half.
Do you expect that the truncation is changing anything important here?
The truncation will give you an effective Hamiltonian to describe the low energy physics in this regime. Now, it depends how many terms you keep in the truncation. There is a transformation. It's like a Schrieffer-Wolff transformation that leads you from this model to this model, and that has, of course, many terms. And if you keep only lowest order term, you get the simple XY model. If you keep higher order terms, you get longer range interactions, but they're presumably smaller by factors of T over U to some higher power. So that's the usual procedure of renormalizing down to low energy. You essentially integrate out triply occupied or higher occupation states, and you're left with the low energy effective Hamiltonian. The low energy effective Hamiltonian of hardcore bosons, essentially hopping these bosons around. I want to add a gauge field to this hopping, so I can couple them to a magnetic field or rotation or an electric field in the case of conductivity. And you see there's these intersite interactions that they want to put in. They will essentially play a role, but not a very important role. And then there's a chemical potential. And this U is taken to infinity to prevent more than 2 states. I want to emphasize that when you take U to infinity, the resulting hardcore bosons are not free anymore. Their commutation relation is not just delta ij, but it has this factor 1 minus 2 ni. This comes from the constraint that we will impose by taking U to infinity. So when does this behave like free bosons? When the density is very, very small, you can neglect this term. But as the density comes close to a half, these commutation relations are definitely cease to be purely bosonic, and it's quite dangerous to use bosonic theories to describe, or simple bosonic theories to directly describe the hardcore bosons. So I'll show you what one can do. You should use the spin and a half XY representation and then you replace A dagger with S plus, A with S minus. The commutational relations of S plus, S minus are precisely these, where the density is Sz plus a half. And now you should think of this model, but it's a quantum model, not a classical model. There's commutation relations, in the path integral you have interesting Berry phases associated with spin a half. So one should think about this quantum model in order to do the dynamics properly. So again, this is the model, and this is the, I'm here throwing away, well, not this is the intersite interaction. It's like an Ising interaction. If V is smaller than the value of T, then the system is really XY-like, anisotropic XY-like. And just to give a handle of what the phases are, if the bosons, this is essentially the round filling of 1/2, you have one boson per two sides. If the bosons are in the superfluid phase, that means that the ground state is essentially delocalized bosons in a condensate with a well-defined phase. This translates in the spin language to a very simple state, a ferromagnetic state where all the spins are lying in the plane, not necessarily in the x direction, they could lie anywhere in the xy direction. So having long-range spin order in this model is the same as saying you have a coherent superfluid in the bosons. On the other hand, if the bosons are localized, in the case of half filling it would be a bipartite charge density wave, that corresponds to an antiferromagnetic Ising order of the spin in the z direction. And you can study the space transitions and the different dynamics of the order parameters exactly like you would in this model. Except that now you can add a gauge field that frustrates the ferromagnetic interaction in the plane if you want to study the effects of the magnetic field. So that's the translation between hardcore bosons and quantum spins. And what do we know about this spin and a half model? Well, if you calculate the stiffness, which is the stiffness to make a twist in the spin as a function of the density or the Sz, if you want, it has a non-monotonic behavior. The superfluid stiffness increases, reaches a maximum at a half, and then comes down to 0. So that means this system is a superconductor everywhere for every filling except 0 and 1. And its maximum stiffness and therefore maximum transition temperature is at a half. That's where it's the best superconductor. There's a symmetry that emerges from the constraint that we put in to the effective Hamiltonian. The symmetry is between n and 1 minus n. That's a charge conjugation symmetry. This symmetry does not exist for continuum bosons, and it comes from the lattice. It comes from the fact that when I have a few number of bosons on the lattice, I should count bosons. When I have a lot of bosons on the lattice, I should count holes. This symmetry, which is a precise symmetry of the Hamiltonian, that they can write down in terms of rotation around the x-axis for the spins, takes a to minus a, and b to 1 minus nb. And with that, you can prove that the Hall coefficient, which is just derivatives of the generating function in terms of a, the Hall coefficient is antisymmetric between n and 1 minus n. Therefore, the Hall coefficient switches sign between below half filling and above half filling. Half filling, sigma h is equal to minus sigma h is equal to 0. There's no Hall effect with half filling. So this is a consequence of the symmetries of the model, and that shows the strong effect of the lattice. How do we generate? Okay.
Is it true for any lattice or for square lattice only?
Good question. For fermions, we know that symmetry is only for bipartite lattices. But for bosons, it's for any lattice, no matter what interactions you put. The transformation that I showed before, okay, is a rotation around sigma x. It takes S plus to S minus to S plus, and that is on any bond. And it leaves the sign the same. For fermions, you have to do a sublattice gauge transformation, and that's only available for bipartite lattices. So bosons have a particle Hall symmetry which is different than fermions, if you're familiar with these words. If I want to treat this model with a field theory, or if I want to evaluate simply its phase diagram and the kind of the mean field I did before, it's useful to use a path integral. Now, as I said, the model itself is a spin, so therefore the correct path integral to use is a spin coherent state path integral of spin a half. People in quantum magnetism are very familiar with these constructions. This is the usual way of constructing a spin wave theory, and it's familiar to people who do bosons in its Bogolyubov theory representation. I want to show here how you start with spins and actually end up with a Gauss-Pitaevsky equation at low doping, at low filling. You see when you write down these spin coherent states are essentially unit vectors on the sphere. They are represented by phi and theta. There's a kinetic term, called the very phase term. And then there's the classical xy Hamiltonian with a gauge field, xyz Hamiltonian. And you represent it in terms of these angles. And these Berry phases produce the dynamics. From this you will get the dynamics of the semi-classical dynamics and so on, and you can do the semi-classical quantization of spin waves. But also Berry phases, to those who are familiar in quantum magnetism, could give you dangerous contributions, like the spin a half model of the Heisenberg antiferromagnet gives rise to gaplessness in one dimension, and Hedgehog Berry phases in 2 dimensions and stuff. So what I'm saying is that Berry phases are something you have to watch out for, and in fact we'll see that they do affect also the lattice bosons in an interesting way. At low densities they don't matter so much. At low densities one can write a complex order parameter built out of a phase and the square root of the cos theta is related to ni. So it's this representation of this Hamiltonian expanded to low order in psi is simply will give you the Gauss-Pitaevsky action. As you can see, the Gauss-Pitaevsky action is linear in time, second order in space, and this would be an approximation to this model at low values of psi. But there's higher order terms. The question is, when do they become important? They become important as we increase the density and go towards half filling. And then this mapping breaks down. Too much if you use a different mapping. So the Gauss-Pitaevsky theory, as we expect, is good for the continuum limit. And this is just textbook material about how you get a vortex in a Gauss-Pitaevsky theory. You add a magnetic field, you get essentially a Schrödinger-like equation, you solve it, and you find that the phase will rotate around a certain point because of the gauge field, and the profile of the vortex would look like that. This is the corrections coming from fluctuations above the Bogolyubov, the Gauss-Pitaevsky using Bogolyubov theory. So this is the density profile of a vortex, this is the phase, and the density profile, as you can see, decays as a power law. That means actually that the vortex core is very large, and if you calculate the charge missing in the core, it's actually infinite. Diverges logarithmically with the size of the system. So that's the particular feature of vortices in the Gauss-Pitaevsky equation. Around half filling, that will change. The vortices will not have a charge depletion at the core, and their core size will be exponentially localized. So it's a qualitative difference between half filling and low filling. So this is applicable to low filling of the bottoms. Now, what I'm really interested in this talk is to show something about transport theory. So let's go back to saying, how do we understand transport in a continuum liquid? Well, this goes well back to hydrodynamics of Magnus. When you have a vortex that actually is imposed here by a rotating cylinder that you put into a liquid, and then you flow a current around this liquid, the rotating cylinder will create a distribution of currents that would produce a hydrodynamic force And that high dynamic force, called the magnet force, is perpendicular to the flow of the current, and is proportional to that flow, and that's the force that acts on any vortex in any system. So that force will also act for continuum bosons and for lattice bosons. It's just a hydrodynamic force coming from minimizing the total kinetic energy of the liquid. But when you look at the dynamics of the Gauss-Pitaevsky, you will get that the vortex will actually want to move. And it will want to move according to the gradient of the Hamiltonian, which comes from the current that you impose, the boundary conditions, the location of other vortices, and so on. And if you look at this equation of motion, it's kind of an equation of motion that similar to a top or an electron in a very strong magnetic field. It's what's called phase-space dynamics. Is the velocity is going to be perpendicular to the gradient of the Hamiltonian and not parallel. So it's non-dissipative dynamics. And in the semi-classical approximation, it means that the motion is always going to be perpendicular to the gradient at i.e. on equipotential contours. So it's a very simple motion, and once you move on equipotential contours and don't dissipate any energy, it means that you cannot get any resistivity, for instance, in a system like that. And if you don't have any potentials, this simply means that the vortices go with the flow. So if you have a current flowing this way, and you have a vortex rotating this way, there is a Magnus force that wants to push it perpendicular. But that will be reducing its energy, and it cannot reduce its energy. It has to go perpendicular to the Magnus force, and therefore just go with the flow. So simple thing to remember is in the continuum, vortices go with the flow. Once they go with the flow, they will produce themselves a Hall voltage perpendicular to their direction and the direction of the current. And if you translate that to transport, you'll say no dissipation, sigma xx equals 0. Going with the flow leads a Hall conductance, and you calculate how much it is. It's precisely, this is NEC, and Q is the charge of the bosons, NQ divided by the magnetic field. So this is a very brief review of what you expect in a Galilean invariant continuum superfluid. Of course, by Galilean invariance, you know that the Hall conductance is NEC over V and Q over V. And here I gave you a vortex explanation of the same result. Okay? So I know this result, as I say, directly from Galilean invariance. Let me forget about vortices. I have a charged fluid. This fluid is moving with some velocity. It sees a magnetic and electric field. I can cancel the effect of the electric field by moving with the flow. I ask which velocity do I have to move in order to cancel the electric field. That's precisely the velocity that will give me this relation. In other words, that will give me the value of the current. Because in the moving frame, this vortex is stationary. So these arguments are much more general than the semi-classical picture that I gave here, but the semi-classical picture is something that we always keep in mind, because as we go to the lattice problem, and the Gauss-Pitaevsky equation ceases to be correct, this result ceases to be correct, we get new phenomena happening due to the lattice.
So is it correct to say that under the state of cuprates you have a very large Hall angle? Is it one of the consequences of that model?
Okay, going back to cuprates, okay, one has to associate, first of all, what are the bosons, what are the charge, how do you count the charge away from
No, just qualitatively. I mean, is it the trend
Qualitatively-
that the Hall angle would increase as you go towards a more insulator?
Yeah, this relation that is always used, you know, sigma xy is equal to n EC over B. So the only question is what n do you measure? In cuprates, you measure the number of holes away from half filling. And that seems to be, actually it's a very old result in cuprates. One measures the number of carriers from half filling. That's not Fermi liquid. You not get it from but it's consistent with thinking of the pairs as bosons with that charge. That's all. When a vortex moves, I said before, it produces an EMF. So this is not just for charged bosons, this is for neutral bosons as well. In a superfluid, pressure drops are created by motion of vortices. The only way you can get actually a pressure drop is a motion of vortice or vorticity. You can see how it works because as you move, the phases which wind around the position of the vortex are changing, and when you look at their time dependence of the phase, you get this kind of dipolar stress tensor field. So each vortex produces a dipole. The direction of the dipole is perpendicular to the motion, and this is the definition of the vorticity current. You have many vortices, and when you add a lot of vortices together, you add all these dipoles together, you get a constant electric field, or it's actually not an electric field, but a stress field that's proportional to the velocity of the vortices, and you get this relation between the vorticity current and the induced EMF, or stress field perpendicular. So when I said before that the moving vortex produces a Hall voltage, it's precisely this effect. And that's general, that doesn't depend on the dynamics, from the definition of the motion. And one way of writing it in a nicer way is the induced field is V over C cross B with a minus sign, it's like the Lorentz force. But it's nothing to do with electrodynamics. It's totally hydrodynamics, what I say. And it happens in a classical liquid as well. How do we get dissipation? Dissipation is more complicated to get. Dissipation is a very interesting property because that's the source of resistivity. Dissipation comes from vortices moving not with the flow, but hopping between different pinning sites. So you need something to break translational symmetry, like a potential, pinning potential, or any kind of variation in potential. A vortex, when it moves from one point to another, changes the momentum of the superfluid. So changing the position of the vortex is the same as saying, I'm changing the momentum, I'm dissipating momentum. Now, how does a vortex move from different pinning potentials? Well, you have to solve the quantum mechanical problem. It's not within the Gauss-Kitaevsky description. You have to write down a wave function, a quantum wave function of a vortex located in one pinning site and located in another. And the tunneling, which is the overlap of these two many-body wave functions times the scale of time scale, which is the pinning time scale, will give you the hopping rate. Hopping rate is essentially the method of which a vortex can lose its momentum and dissipate, or change its position and dissipate momentum. So this is a very important ingredient in asking about mobility of vortices. As you can see, if the vortices don't see any potential, they can't move. They can move with the flow if there's a flow. If there's no flow, they can't move. But if you have pinning sites, there's a quantum mechanical probability and it's a tunneling probability. It decays as a Gaussian, actually, of the distance between the pinning sites.
But you're also assuming that there is no dissipation coming from the core.
Right.
I mean, there's no pinning.
Right. This is pure bosonic now.
So, but is there
No.
any dissipation in the core? Just
Yeah, the dissipation is, in fact,
no,
the,
without pinning, Just a single vortex which moves. I mean, usually there is a dissipation coming from the core.
you talk about superconducting vortices? Or boson?
Superconducting.
Yes, so here I'm not discussing superconductors anymore, I'm discussing just the boson model with no electronic excitations in the core, okay? The only excitations I have are the boson phase fluctuations.
But the wave function goes to zero in the core, so
Right.
there should be.
So the condensate wave function goes to zero, but that's, again, a semi-classical picture. The quantum wave function of the vortex is actually not exactly localized in one point. It's like a superposition of, coherent states in different positions. But the calculation that we did for the overlap, okay, used essentially the semi-classical expansion. We used the coherent state plus the Bogoliubov fluctuations, calculate the overlap, and that overlap is, as I said, a Gaussian of the distance. The characteristic length scale of the overlap is the distance between bosons. That's the quantum length scale of this.
Does the vortex have a mass here? Is it massive?
Okay, so this is the generation of the mass for the vortex. See, without this spinning potential, the vortex can't move. It's like a particle in the lowest Landau level with infinite omega c.
But what determines the value of the mass?
Of omega c?
No, of the vortex mass. How
Okay,
do you-
so the value of this generated mass, and the mass is generated by the existence of the pinning potential. As I said, without pinning potential, there's no tunneling. There's no. It's very similar to a particle in a very strong magnetic field. If you know that problem, then if you think of the particle in the lowest Landau level, it has essentially, if you want, zero mass, which is it's frozen to sit in a cyclotron orbit of the Landau length. But if you put a potential, it can tunnel, and now it can dissipate and give you a finite resistivity. It's a very similar thing with the vortex. In the presence of variation in potentials, or if you have a superfluid and it's flowing in a channel and there's some disturbances at the borders of the channel, breaks translational symmetry, then you can have tunneling processes. The tunneling process itself will give you a hopping between these two. You call the hopping an inverse mass, if you want.
So without the pinning potential, does it make sense to talk about mass at all? Or
Yeah, you can say the mass is zero. Then you get pure phase-space dynamics.
but is it potential dependent, the mass, or is it something which is related to the
Yes.
potential itself?
Yes, the mass scale actually depends on the potential. But by this definition, you see there's lots of definition of mass which are very confusing. This I think is the useful one, because this one tells you how much transport is going to happen due to the motion of the vortex. So what you get from this is mapping the vortex motion into a hopping problem. And the hopping rate in this hopping problem, if you want to call it mass, is given by these overlaps, by these distances, and by the pinning potential. So this is just a useful definition.
Do I understand correctly then that the effective action gap is the coefficient in front of the r dot squared in the effective action?
Yes, and now, right, I think it's better perhaps to think of a lattice hopping model, where you hop between pinning sites. You
So
can
the-
take the continuum limit of that model and get a second order.
Yeah. But this calculation, was that done on the lattice or
Yeah, no, this was done just between two pinning sites.
pinning? Yeah.
Now, this is an old calculation just to show the scale. What I want to show is just the scale. The scale of this hopping is dependent on how far you have to hop. So if you have, two spinning sites on both sides of the sample, there's zero chance that you can hop, and that's why superconductors are good superconductors. But if the distance here is microscopic, it's of the order of the distance between bosons, then these numbers can become large, and the hopping can become significant, and then you get dissipation. And the system ceases to be a good superfluid. Notice that if we had a lattice underneath these bosons, and the density of bosons was about the same as the lattice constant, we'll be in the worst situation in terms of, or the best situation in terms of hopping, because these numbers will be about the 1. That's what happens for hardcore bosons at half filling. That's the only message I want to say. Hardcore bosons, when you make them 1 per every 2 sites, are in the limit of very strong vortex tunneling. So vortices of hardcore bosons on the lattice are very mobile. They're very easy to change their position. Now, if you have a lattice, you ask, you have translational symmetry. Why would you get dissipation of momentum? The reason is because real momentum can translate into Umklapp scattering, and if the Umklapp wave vector, which is the inverse wave vector of the lattice constant, is commensurate with the density, that will give you essentially a possibility of mobility of the vortices on the lattice.
So does it mean that you have kind of a depinning transition here, like when your superflow is
Okay, the depinning is now the question about many vortices. Let's discuss that. But the single vortex, in principle, can.
No, I mean if you have a flow which is fast enough, you can depin the vortex from the potential, and then you will see something experimentally. Is it?
Sure. Yes. The moment these vortices can tunnel around, there's dissipation, there's resistance at even very weak currents. The reason a superconductor is a superconductor is because you also have interactions between voltages, and it's a lattice, and it gets pinned much stronger than a single voltage does. But I just want to summarize what we learned from the continuum. The voltage is localized on equipotential contours. They drift with the superflow. The Gauss-Pitevsky cannot treat the short-range potential effects, and the short-range potentials delocalize the vortices and make them quantum. And now we want to go to the opposite limit, where the lattice is very strong and the vortices are very mobile, and ask, can we calculate anything there? So at half filling, I apologize to people who are not familiar, and I know that this is not all of you are familiar with the quantum magnetism, but it's just that the analogy is so useful to go back and forth between quantum magnetism and hardcore bosons, that I make a reference to those who know what I'm saying, that the physics of the quantum antiferromagnet is very close to the physics of hardcore bosons around half filling. There's this way of writing the spin direction, the unit direction of the spin that I described before, in terms of two fields. One is called Canting, and one is called Niel. And when you write down the Hamiltonian, you end up with what's called the nonlinear sigma model. What is important about this model for our purposes is that it's not first order in time, but second order in time. That's extremely important for all the Magnus and Hall physics, because the relativistic second order dynamics does not have essentially the physics of a Magnus force or Magnus action on a vortex. That comes from the Gauss-Pitevsky from having a first order in time term. But at half filling, that first order in time is eliminated, and there's only a second order in time leading second order in time term. This is a relativistic theory. Some people can call it relativistic Gauss-Pitevsky, but I would prefer to call it just the nonlinear sigma model. That's its older name. And it's a model that describes a ferromagnet in any dimension or an antiferromagnet, doesn't matter at this point. I do keep the gauge field in the XY directions. There is an anisotropy built in for the Z direction. So this n vector is actually lying in the plane and has massive fluctuations out of the plane. Therefore, the core, which comes from rotating the spins in the n direction, in the Z direction, is exponentially small because this is massive. Actually, this is the mass. The mass in the Z direction ensures that the cores are small, and that's different from the large core of the Gauss-Pitevsky.
I saw.
Yeah.
So when you do the mapping, the gauge field also transforms? So the spins see a different gauge field?
In the XY direction, the gauge field stays the same.
So the spin field is the same gauge field as the hardware bosons?
Yes, the spins in the XY direction. In the Z, there's no gauge field because that's the density direction. In the XY, that's the phase direction. So, okay? Yeah.
I also have a question. So if you take the original lattice and do some sort of duality transform with the bosons,
Yeah.
you will get some vortices. Are these the same vortices you're talking about that would arise from the sigma model, or is something different?
Well, the vortices will be the same vortices in the sigma model. It's an anisotropic sigma model, so it's an XY model essentially. The only difference between Gauss-Pitevsky and the sigma model is the second order time derivative. But if you look at statics, it's the same. Just ask about the static configuration.
So these are the same objects you're talking. They can cross over from one another. In some
Yes,
sort
the
of
difference
procedure.
between Gauss-Pitevsky and the sigma model is in the interpretation of what the order parameter is. In the Gauss-Pitevsky, we have this relation that is not general, that says that psi is the square root of the density e to the I5. But at half filling, that's not the order parameter. The order parameter is, let's call it delta, just to have a different name. It's some number, which let's call it magnitude of delta, e to the I5, and this has nothing to do with density. Okay, it's important to remember that, because the connection between the amplitude of the other parameter and density is only good at very low filling.
So do the vortices see an effective dual magnetic field sort of when you do this with this transform
Yes.
associated with
Yes, the Berry phases will come out to be right. I'll discuss the Berry phases later, of course.
So this magnitude of delta approaches in the lower density limit approaches the regular density, right? And when n equal 1, you basically approach 1 minus n. Is that the case?
No, the delta is a number that can
Delta is like
vanish.
this, right?
The delta is a number that can vanish even though the density is a half.
Right. So
It's not a
delta
constant.
is basically it's kind of similar to the curve. It shows like it's like a parabola downward, right? It's from 0 to 1 when you have the thinning. I mean, suppose you plot the thinning from 0 to 1.
Yeah, delta is the projection of your spin onto the xy plane, but it's not the magnitude of the spin.
So
Understand?
delta traces the value of superfluid density. Is that the
Superfluid
case?
density is another quantity. Superfluid
But
density is the
It's
stiffness.
related to this one, or not?
No, superfluid density is related, but it's not that number. Superfluid density is a response function to twist in the plane.
Right, but
It might be
superfluid-
0.
yeah.
It's usually 0 together when delta is 0, but it might have different temperature dependence. It's a whole subject by itself. The superfluid density, okay, measures the response to a gauge field in the
Right,
plane.
but usually in this simple case, the superfluid density will be the total density.
Yeah, the relation maybe you're discussing with this is something like delta squared.
Uh-huh.
Of course, you need the coupling constant. Let's call it zero temperature or something. That is a mean field relation. And it ceases to happen. Now, the Kostelis-Thales transition, this is 0 actually.
Right.
Because I don't want to confuse people too much. This is 0, but this is finite. So I have to be careful about this relation. It's only mean field. Erase it. So all these signs means that we have to do a calculation to get the Hall coefficient, not from semi-classics, but just solve the quantum model. How can we do it? Well, you could put the full many-body boson, hardcore boson model on a torus with a square lattice and penetrate the torus, essentially by imposing a gauge field on these bonds, with a uniform magnetic field. And this is a fascinating mathematical system that we learned a lot from. Actually, we learned a lot and we surprised ourselves and other people by different results. If you want to do that on the torus, you want to penetrate it with a uniform magnetic field, you'll have to break the symmetry of the torus, even if the magnetic field is uniform. That's a surprising result. I can go back to that point later if you want, but there is an automatic necessity to break translational symmetry both in the x and y direction. These two lines are the lines that show me why the symmetry is broken. These are lines of zero flux. If you take the ADL on this line, ADL on that line, they're 0. There must be two lines like that. They're called null lines for one flux quantum in the torus. Their intersection is the null point. That's the point where two null lines intersect. And then the system will produce, okay, and then I can add, what this includes adding Aronoff bond fluxes in the two holes, which I'll use later. Opposite the null point, there'll be a vorticity center. That's where the vortex would want to sit. So I'm talking about now exact many-body wave functions. The vortex is a semi-classical construction. But the center of vorticity will have to be opposite the null line, just by the choice of these two null lines, which is a choice we have to make, a gauge invariant choice. I can move the null line by changing theta x and theta y. So you can move the vortex anywhere on the torus by changing these two Aronoff bond fluxes. So you have a handle on where the vorticity is. Why do I want that? Well, it turns out that when you do the semi-classical analysis of this vortex wants to sit here, but it has quantum mechanics. It wants to sit here, but it has a confining potential. The semi-classical vortex feels a confining potential around RV. From semi-classics, we know what the confining potential is. And we can look at the spectrum. So what we have the confining potential, we have the spectrum. From that we can compute the vortex mass. Because the vortex is like a particle sitting in a quadratic potential, and it will give us a list of states. How do we get the vortex hopping rate? Well, the way we did it is we write the vortex hopping model with an unknown hopping rate, so we're not calculating it like we did before semi-classically. We're leaving this as a free parameter. All we know is the vortex hops between the dual lattice points with a gauge field that is given by the boson density. That's this duality of vortex charge. So we have the Hamiltonian, we have this confining potential I discussed before, coming from semi-classical arguments, and we can look at the spectrum of this Harper Hamiltonian. It's a Hamiltonian of a lattice with gauge field, and compare it to the exact many-body spectrum. So what we're looking at is a Harper equation and a confining potential centered around the vortex position. We know this K, that's 39.2 times the number of bosons, and it scales down with the size of the system, and we can now fit the spectrum. The spectrum looks like, okay, this is the hopping rate we want to extract. The spectrum looks like these states. Soon I'll describe this double degeneracy, which is very interesting. But if I ignore this double degeneracy, I look at these three states. I want to associate them with the three low-lying states of this model. That'll give me TV. And TV is essentially the vortex mass on the lattice. What is the value of this TV? Well, roughly speaking, the vortex mass of this hopping rate is essentially the same as the boson mass. It's a very light vortex. Okay, so vortices are quite mobile. They have a
So you're
large
considering
hopping rate.
strictly 2D vortices, not
2D.
not
Completely, yes, yes. Completely 2D. In 3D, it increases with the exponentially with the size of the extra direction. So this is how we extracted the mass. So we found the mass is quite light. If the mass is light, that has implications for experiments, because vortices at t equals 0 with their 0-point motion might be in either a vortex lattice phase or a vortex liquid phase. And now we can estimate where is the phase transition between vortex liquid and vortex mass. To confirm that we're not just fitting two different things which are not related, we can plot in the many-body wave function the vorticity density. That's essentially the curl of the current in the states we discussed, and these are the three localized states. The ground state, the first excited state, the second excited state. And you see there's a vorticity density map. And this is the single vortex wave function of the Harper model, just psi squared, the probability density. And you see, it does look quite similar. Of course, you don't have too many points. It's not. So to show qualitatively, you get even some of the features here, this kind of node in this direction. So the wave functions of the vortex, now we're talking about quantum vortex wave functions, is quite well reproduced using the mass that we extracted. Yes?
So where, this exact solution, where does it come from? So you match this Harper model to...
This is numerical. Exact solution is a hardcore boson.
It's, okay, it's a finite system and you just solve it.
Finite 4x4.
Oh, it's 4x4.
Right.
But it's
16
pretty
side. We
small.
also did the 4x5, but this is the best. It's a single vortex. Its physics is quite short range, so I think the numbers are okay. You know, it would be better if we had a 20 by 20.
And so this mass doesn't depend on the geometry of the system and on the system size, etc., etc., etc. Is it
We didn't have enough, you know, different system sizes to check that. All we wanted is an order of magnitude for the mass, because previously there was no estimate what order of magnitude you get. So, you know, I'm sure that finite size effects are very strong here, but at least the order of magnitude, I think, is okay. So the vortices are quite, as you say, low mass. Quantum melting. If you have a vortex lattice, the classical model for vortex lattice, this is just from semi-classics, let me forget about the kinetic energy. It's a logarithmic interacting system with a background neutralizing charge. There's some retardation effects that I'm ignoring here, coupling to the phase fluctuations. This is the multi-vortex Hamiltonian that people write down. If you add the kinetic energy, those vortices would have zero-point motion. One can ask, at what value of the density would this melt? So we could do a Lindemann criteria, but Lindemann criteria for melting is very rough and gives you essentially no good estimate, because the values of the Lindemann criteria could go between 100 to 1. So the better way is to look at simulations which were done on this particular model by Monte Carlo, which found melting at some density, essentially density of vortex, which is around 12 actually. Yeah, RS equal to 12. So you remember in the electronic problem, there's this Wigner crystal melting at RS equal to 37. RS is the dimensionless ratio of some density or distance between particles and some quantum length scale. Here, it's a different dimensionless ratio, but again, it's something that reflects the strength of interaction and the mass, and you can see it depends on the mass. And at this value, it was estimated that the solid, or the superfluid, if you want, turns into something else. So if we translate our numbers of the mass into this criteria, we get that the vortex lattice should melt at around 6.5 10 to the minus 3. So it's around 1% to less to 0.5% of a vortex per lattice side. That's a very low density. So you don't need strong magnetic fields to destroy the superconductor or the superfluid, or the two-dimensional superfluid with such large popping rates.
So you here disregard thermal fluctuations. At what
This is T equals 0.
Yeah, at what temperatures would
Yes.
thermal fluctuations?
Right. Yes. Thermal, this model, okay, well, I'll show soon, this model without the quantum effects has a melting temperature which is independent of density in the classical limit. Okay? But if you put the quantum fluctuations, that's not true anymore, because you can have quantum melting.
I'm
So-
confused. That should be a repulsive interaction, right?
This is logarithmically repulsive interaction, yeah?
No, that's attractive.
Ah, yeah,
Yeah.
sorry.
And then the background charge is
That should be
repulsive.
positive, that should be
Yeah,
negative.
so they're both
Sorry,
flipped.
sorry, I guess I wrote a Lagrangian before. Sorry. Yeah, this is minus and plus. So this logarithmic Coulomb gas is an interesting model. We're actually studying it these days. One thing is known about it from Agro and Sepperly, that when it melts, it doesn't form a superfluid. So the vortices don't form a superfluid of vortices. At least they don't form a Bose condensation of vortices. What is it exactly? What is that phase is an open question. Is it an insulator, or is it something else, perhaps a Bose metal? But let's leave that question open. We at least found that it can happen at quite low densities of vortices. In cuprates, by the way, they've seen a vortex liquid phase. And again, well, we always come back to cuprates because I think that's the best example of a bosonic superconductor. And in fact, a lattice boson superconductor, this is kind of a confusing plot, but what you have here as a function of magnetic field, you have a phase which is a superconductor, this vortex solid, and then you have a vortex liquid, which is actually a metal, or a resistive state. What you see here is different melting temperatures. So at T equals 0, here you cross between a solid and a liquid. At higher temperatures, you could cross between a solid and a liquid at lower magnetic fields. But if you plot the temperature as a function of magnetic field, you see the melting temperature goes down until it hits 0 at some critical vortex density. If you just looked at the classical model, of course, as I said before, by scaling, the melting temperature should not depend on density. So this is strongly quantum tunneling effects. This means that the vortices have a finite mass, and they're melting because of quantum fluctuations. So what is that phase? As I said, we leave it open. What kind of a vortex condensate you have in cuprates. How am I doing in time? I don't know. You are the postman.
Yeah, posing state constraints, how much time do you need?
I think 10 more minutes will be okay. So, because now we're getting into the interesting stuff. The Hall coefficient can be measured by what's called the Chern number. You exactly diagonalize the Hamiltonian on this lattice I described before, on the torus. You look at derivative with respect to Aharonov-Bohm fluxes, take this adiabatic curvature, integrate over all the different values of theta. It's a large numerical calculation, plus you want to do it for all the states with the Boltzmann weight, you do it for the low-lying states, and then we get the following result. The Hall coefficient as a function of density goes like this. It increases linearly up to half filling. It vanishes at half filling by particle Hall symmetry. Then it flips sign and turns into a whole system with the opposite Hall coefficient. The continuum model, as I said, is just linear all the way. So here you see the lattice effect coming in very, very strongly at half filling, vanishing the Hall coefficient, reflecting sign. That's the interesting effect. Now, what we find from numerics is that this transition is very abrupt, but as you heat, it becomes smoother. So you can associate the temperature scale. This is the Hall coefficient as a function of temperature, and this temperature scale seems to vanish at half filling. Seems like quantum phase transition. But of course, we're talking about a small system. We can't make a statement about quantum phase transitions here, but there seems to be a vanishing energy scale or temperature scale at half filling. So half filling is a very strange point here. And that point is something we studied a lot. We studied the properties of vortices here, and also the conductivity and the resistivity there, but that's a different story. So this particular point is what I want to discuss in terms of vortices. I just want to mention kind of an illustration why it's a strange point. If you consider half filling as a bunch of holes and particles, and you have a particle current moving one way, and therefore the whole current moving another way. If you go back to Magnus dynamics, you know that the vortex always wants to go with the flow. Question is, what is the flow here? Because if you put the vortex here, first you should look at the flow and you see that it's both hole going this way and particle going that way. If you put the vortex here, it's a vortex of particles and an anti-vortex of holes. So the vortex of particles wants to move with the particles, the anti-vortex of holes wants to move with the holes. So it doesn't move anywhere. It can't move, and that's the reason the Hall coefficient vanishes at half filling. It's an illustration from Escher for particles and holes moving in opposite directions. But I think there's some interesting cold atoms experiment one could do. You could take a rotating, now I don't know how to do that, but rotating optical lattice, have a gradient of a density. Here you have density below half, here you have a density above half. That actually is, I guess, where you have these transitions between the wedding cakes, when you have a below half and above half. And the claim is that the vortices here will have completely different dynamics than the vortices here. Here the vortices, if you pass a current, if there's any kind of a imbalance of particles, they will move with the current, but here they'll move opposite. Here they move downstream, here they move upstream. That is consistent with this kind of a, and the transition should be rapid because of this fast transition we find in our numerics. So,
But that can produce hydrodynamic instability. Like you have two liquids moving like that.
it's the vortices that move this way.
Right, but that's the same thing. You have
Okay,
two
so-
flows moving like that.
So you
it's
get
usually
all kinds.
unstable.
Yeah, could be interesting. Anyways, that's just an idea that we thought might be relevant to cold atoms. Degeneracies. If you looked at the spectrum at half filling, as a function of our Aharonov-Bohm theta x, for instance, keep theta y constant, change theta x. We found large number of crossings of all levels. And these particular points where these levels crossed were some values, fractional values of these thetas. All the spectrum had level crossings. There was double degeneracy in all the spectrum. So it must come from some exact symmetry of the problem. But it took us some time to find those symmetries. Those symmetries that lead to the degeneracies happen when you have a magnetic field with odd number of flux quantum into the system. And as I said before, when you tune those numbers and you look where does the null point live, or where does the vortex point, but more importantly, where does the vorticity center, this is exactly when the vorticity center is on a lattice site. So these points are not just arbitrary, they're the ones who place the vorticity center on a lattice site. So we proved that indeed this comes from a symmetry. But the symmetry was not a magnetic translational symmetry, as you have in the Harper equation, it's well known, but it's a point group symmetry, and these are the operators we call pi operators. We just got the, I have to boast, I got a referee report that, accepted the debate with Physref B, but he said, that he called these operators fantastic, sorry. They're a combination of three operators. First of all, reflection around the x and y axis. Charge conjugation symmetry, particles to holes, but we're sitting at half filling, so it's a point of symmetry of charge conjugation operator. And a gauge transformation to fix the gauges after you do the reflection and the charge conjugation. When you take the combination of these three operators, and this phase that goes into the gauge transformation is chosen from the gauges that we had put in the system. So it's not gauge invariant, it depends on the choice of the gauge. When you take these three operators, you find that there are symmetries of the Hamiltonian. They commute with the Hamiltonian. Both pi x and pi y. That's not surprising. As I said, the problem is charge conjugation symmetric, and the lattice is reflection symmetric, and the magnetic field is the same everywhere. So up to a gauge transformation, that should hold. What is more interesting is that they don't commute with each other. Sometimes. When the number of flux quantum is odd, they anti-commute. And out of two of those, you can create a third one called I pi z, and you can show that these guys are just the three generators of SU2. You can prove, therefore, because of this minus sign for odd number of vortices, that any state of energy, which will also be an eigenstate, let's say, of pi x, will have an orthogonal partner with minus pi x with the same energy, and therefore all states are doubly degenerate. That's the usual proof when you have a non-abelian algebra of symmetries, that you get degeneracies. So here we prove that
something like Cramer's degeneracy?
not precisely. Cramer's degeneracy is related to time reversal invariance, and it's a bit of a different proof, but it's similar. Yes, it's doublets. All spectrum are doublets for odd number of particles. When we use that, okay, we ask, what does this degeneracies mean? Well, it's been known from variational calculations of Schucheng and his group, and by others, that in the center of the vortex, there's a charge density wave. This is a profile of the charge density wave. And charge density wave can be pointing either in the up or down direction, because there's two charge density waves. So spin up in the z direction is really related to a charge density wave in one particular registration, and the other registration is spin down. But of course, the degeneracy means that you can make superpositions of these two spins with no charge density wave, and you get essentially a quantum number associated, SU2 quantum number associated with each vortex. And this variational calculation and Berry phase arguments leading to charge density wave of the core were done before semi-classically. But the operators that we showed before will allow us to apply this degeneracy to a collection of vortices. Arbitrary odd number of vortices will have this double degeneracy with interactions and not relying on any approximation. This exact result for any finite system. And why is it important? Because we want to know not just that there is charge density waves in the cores of vortices, but also what are the excitations. And the excitations are going to be like excitations of spin halves. The demonstration of how it looks like is here, where you have spin up, spin down, and spin pointing in some direction for each vortex. Those spins interact. There's some entropy associated with disordering them. They can order, they can disorder, and they add to the specific heat. And this is essentially new physics that emerges at half-filling. I don't have time to talk about resistivity, but the resistivity is also very interesting. It has this kind of feature of linear resistivity that they see in cuprates. And there's a long paper that was written not too long ago that calculates the resistivity of hardcore bosons using a new method of evaluating the Kubo formula, dynamical Kubo formula, in regimes where Boltzmann equation breaks down. So to summarize all this business in one sentence, hardcore bosons give at half filling have the maximal TC. They're the best superconductors, but they're the worst metals, because the moment you kill superconductivity by phase fluctuation and by vortex creation, the vortices scatter against each other very strongly with a mean free path, which is one lattice constant. So there's no regime we can use Boltzmann equation above TC. So the normal state properties are also quite interesting. They're strongly scattered liquid with definitely linearly increasing resistivity. Looks very different than any Fermi liquid or good metal that we know. And I don't think I can add any more now. So let me just summarize. So the vortex tunneling is enabled by pinning in 2D. Lattice scattering enhances the quantum melting of the vortex lattice phase. Hall effect reverses sign at half filling, and the spins acquire the spin a half V-spin degeneracies, which are interesting. And then the free vortices strongly scatter to produce bad metal resistivity. So thank you very much.
So actually, I have one question will come. So from your final summary, it looks to me your model really give a picture consistent with the ITC phase diagram, right? So it's a poor metal, but it's a very good superconducting state.
Well, the similarities.
ITC, yeah. Is that
it's an oversimplified model, very oversimplified model.
Right.
But it has some features.
Because a vortex liquid, which is poor metal, which
Right.
has been seen by Ohm, right?
Yes.
And below the TC you have the superconducting state. However, so my question is, how do you get this gauge field in other contexts? If you start with Kubo pairs, you need a gauge field, right?
Gauge field
For the bosons. So
that's
the bosons
the
will map to
electromagnetic gauge field. It couples to charge. It's just charge 2E instead of E.
Over there you don't have, you do not have gauge field over there. So you do not have
In a superconductor,
I mean, suppose you're not providing magnetic field by itself. You're relying on some kind of spontaneously generated gauge
no.
field.
This is not a Chern-Simons transformation or something. This is considering charged bosons, okay? Charged boson coupled to an electromagnetic field. The electromagnetic field will induce vortices like it does in a superconductor.
Yeah, but for the height phase diagram, if I don't apply the magnetic field externally,
Right.
so what do you get in the gauge field?
Zero.
Yeah. So the question is how you get your model to describe the picture.
No, my model. Okay. My model is meant to calculate the Hall coefficient at vanishing magnetic field.
Okay.
I only put 1, 2, 3 flux quantum in the whole system and take the derivative to get, or take essentially the linear magnetic field Hall conductance. We could also look at the strong magnetic field Hall conductance, and there's all kinds of oscillations which I think come from finite size effects. So I didn't look at the strong magnetic field limit, which is an important limit also, but the very weak magnetic field limit, just to see what the Hall conductivity is in zero field. And it's already interesting there that it has the sign flip. See, very difficult to get this sharp sign flip from Fermi liquid theory. And in fact, there is a sign change of Hall conductivity. But there's other problems of Hall conductivity we don't know how to answer, like there's a sign flip of Hall conductivity as a function of field and temperature that we don't know how to treat. So I don't think we have all the answers for the cuprates, but at least we have a proof of existence that you can get very non-Fermi liquid sign flips and other phenomena from hardcore bosons.
Right.
Okay, that's
I mean,
the
at
point.
least for the charge sector, it's fine. I mean, it seems to me fine, but for the spin part, it's not here yet.
The spin of what?
Like
The-
in the cuprates, you have the spin gap.
Yes.
You have this,
yes.
like spin resonance.
This is
part.
just the charge
Just the charge
sector,
part, yeah.
and it's only for transport of charge and not for the magnetic correlation case. So that-
What is the quantum statistics of the vortices with this SU2 spin? that we get?
This was something that we thought about, and then we changed our mind after a while. In the beginning, we thought that the spin and a half introduces Fermi statistics between the vortices, like a spin statistics theorem. But it's not true, because spin statistics theorem really relies on relativistic physics, and it relies on 3 dimensions. So the statistics is bosonic.
So you have
these are
bosons
bosons
with
with spin
SU2
and a half.
spin.
What?
bosons with the spin 1/2.
Yes. Bosons with spin and a half.
Yes.
Now, of course, bosons with spin and a half plus spin orbit can give you funny sign changes as when you commute two objects. So it means that you can get effectively more complicated wave functions out of these guys than you get out of spinless bosons. But you can't say that it's just a Fermi liquid or just a free fermion system of vortices. That's not. The story is more complicated. But okay. The question of statistics of vortices has been left open in the low density, in the Gospi-Kajewski. Haldane and Wu, I think, explained that because the charge at the core is infinite, there's no well-defined statistics of exchanging two vortices. But here, the vortices are small and they're bosonic.
So regarding this infinite charge, I mean, you usually charge is screened. So
Right.
I mean, how does that happen?
So you have to have Coulomb interactions,
Right.
and
So
and
generally-
you will get a small vortex core. Yeah.
Yeah. That,
So we didn't do
Okay.
the Coulomb interaction.
So my simple question is that if you're saying that lattice effects are very important here, in the same way I would say that impurities will also be very important.
Sure.
So how would impurities, let's say, what do they do? Do they localize bosons?
No, they delocalize the vortices.
No,
They-
for bosons. If I start with bosons first and then...
Yeah, they
and
localize the
I add
bosons and
random-
delocalizes the vortices, right? It's the same thing. Impurities want to localize bosons and delocalize vortices. They want to push you into the insulating or less superconducting.
Is it, can it be calculated or somehow?
We didn't try, but for this, we didn't do this order.
So would it change the linear resistivity qualitatively?
Yes, I think it might change the linearity, the impurities. I think the linearity is only for the clean system.
No, I mean, linearity usually happens when you're at the optimal doping. As you go away, it becomes
Right.
linear. And that is consistent with what you're saying.
Right, but, okay.
Technical question on what you said on the torus. I mean, that it's true that you break translational invariance, but you said you characterized it by these zero flux.
Yes.
So what flux was it with?
It's a gauge invariant Wilson loops that you can form around the torus. And because you have a magnetic field penetrating, those Wilson loops have,
Oh, so it was just the, you called it flux. It was the Wilson line around.
it was a Wilson line.
Okay,
at zero.
okay, fine.
Yeah, if you cut through that line, there will be no flux passing through it, so it's two special points. There's an interesting objection that was raised by Adi Stern, actually, that said, I can construct for you a magnetic field that cannot break translational symmetry. And we wrote a whole appendix disproving his construction. It's not simple. But his idea was, I would just form a continuous line of monopoles, anti-monopoles in the center, and take number of monopoles, anti-monopoles to infinity, keeping n+1 monopoles and n anti-monopoles. So you have overall one monopole, but its field will radiate radially, and therefore I can't see how you can break the symmetry around the torus. Okay? But it's a false argument. It's a really subtle issue about the fact that the monopoles or the gauge field is static and cannot be smeared. The Dirac monopole is a point object in the classical electrodynamics, and if you take any kind of a polygon of plus and minus charges, where the number of this guy is n and this is n plus 1, there will be broken symmetry on this construction. You cannot make this rotational symmetric even in the limit n goes to infinity.
It's clearly a tricky problem because you're adding and subtracting ones, basically.
Yes.
So
Yes,
it's not-
and quantum
doesn't look
mechanics,
convergent.
unlike classical mechanics, quantum mechanics is sensitive to e to the I phi of x. This could be a horribly oscillating function. This is the flux as you go around the torus, horribly oscillating, but if it jumps by 2 pi all the time, the quantum mechanics sees this as a smooth function. This function breaks symmetry, while this guy, if you average it even a tiny bit on x, will give you a constant.
Does it make sense to put it on a sphere, this problem?
On the sphere, there's no broken symmetry. It's topology. If you put the monopole in the sphere, okay, the Dirac string example, symmetry is not broken because the monopole is at the center of the sphere. The price you pay is all states become doubly degenerate, and you can put your vortex anywhere you want by choosing the right combination of the U's and B's Dirac monopole harmonics. On the torus, you have to choose where to put the monopole. So you put it here, right? Because all the flux of one flux one has to end in a monopole. If you put it here, then you already broke symmetry because the flux will exit, and there will be a point here of zero flux that is chosen by the position of the monopole. So all these things that happen in 3 dimensions affect the physics of the 2 dimension in a funny way.